Here we discuss Bose-Einstein statistic, firstly explaining some important characteristics features, and then we derive Bose-Einstein distribution law. Here we give some important characteristics feature of Bose-Einstein statistic. We know it is a quantum statistic. In that statistic, all particles are identical and indistinguishable. Such a particles must have zero or integral spin. The particles like photons, deuterons, phonons, and pi mesons, helium atom at low temperature, all these particles are known as boson particles. In that photons, deuteron that having spin 1, while phonon, pi meson, helium atom at low temperature having spin 0. Such a statistic does not obey Pauli exclusion principle, or it is not applicable for Bose-Einstein statistic. Therefore, the boson particles are distributed in discrete quantum state, and there is no restriction for the occupancy of number of bosons each in quantum state. Suppose Gi represent number of quantum states that having same energy Ui, therefore all quantum states are assumed to have equal a priori probabilities. Now we derive Bose-Einstein distribution law. Let us consider Ni indistinguishable particles are distributed among Gi quantum state and no restriction to the number of particles that may occupy any of Gi quantum states. For example, suppose we choose 10 indistinguishable particles and these are distributed within 6 quantum states by following arrays of lines and dots that is shown here. Line represent quantum states and dot represent the particles are contained in that quantum state. Here the first quantum state which contain 2 particles, second quantum state 3 particles, third one only 1 particle, fourth quantum state is empty, and fifth one we say that here it is contain 4 particles. Total number of particles distributed within 6 quantum states are 10. Here we consider Gi represent number of quantum states and Ni represent number of particles. Sum of these two represent the number of objects in that array. For that, we keep the first line or quantum state fixed. Therefore, remaining objects will be Ni plus Gi minus 1, and they can be arranged in number of possible ways or permutation of Ni plus Gi object within this array of lines is Ni plus Gi minus 1 factorial. If Ni plus Gi minus 1 factorial gives the possible permutation means number of possible arrangements among Ni plus Gi minus 1 object. Also we find what is irrelevant permutations. The permutation of Ni particle among themselves is Ni factorial, and permutation of Gi minus 1 lines among themselves is Gi minus 1 factorial. Therefore, both terms like Ni factorial and Gi minus 1 factorial becomes irrelevant permutation. Why it is irrelevant? Since the permutation of Ni factorial and Gi minus 1 factorial does not affect the distribution of the particles within the given arrays of the line. Hence, to calculate possible ways of arranging Ni particles in Gi quantum state by taking the ratio of possible permutation to irrelevant permutation. This number of possible ways in GI quantum state, we write Wi is equal to Ni plus Gi minus 1 factorial. It gives the possible permutation, and Ni factorial and Gi minus 1 factorial, these are irrelevant permutation. Ratio of these two gives number of possible ways of arranging Ni particle in GI quantum state. Now, then we calculate the total number of ways of entire distribution of n particles. That n particles, we write number of particles, we start from I is equal to 1 to k, W is equal to product. Product indicate these different probabilities we just choose here are multiplicative. Therefore, the product I equal to 1 to k, Ni plus Gi minus 1 factorial divided by Ni factorial into Gi minus 1 factorial. See, this is the equation number 1. Here, Ni plus Gi minus 1, these are total number of objects that are equivalent to, we suppose Ni plus Gi. Here, since Ni plus Gi is very greater than 1, hence we neglect minus 1, hence simply Ni plus Gi. Therefore, the equation 1 becomes W is equal to product I equal to 1 to k Ni plus Gi factorial divided by Ni factorial into Gi minus 1 factorial. Say this is the equation number 2. Simplify the equation 2 by taking log on both sides. The equation becomes log W is equal to summation. Product becomes summation. If we take log on both sides, log Ni plus Gi factorial minus log Ni factorial minus log Gi minus 1 factorial. Then we use the Stirling formula. Log n factorial is equal to n log n minus n. Therefore, equation 3 becomes, equation 3 we again write here, log W is equal to summation log Ni plus Gi factorial minus log Ni factorial minus log Gi minus 1 factorial. Use the Stirling formula and simplify. The first term use Ni plus Gi into log Ni plus Gi minus Ni plus Gi. For log Ni factorial, it gives Ni log Ni minus minus plus Ni plus Ni. And for log Gi minus 1 factorial, it gives Gi minus 1 log Gi minus 1 minus minus plus Gi minus 1. Simplify this equation by using the next term, Ni minus Ni plus Ni cancel, plus minus Gi and plus Gi cancel. Remaining term we write summation Ni plus Gi log Ni plus Gi minus Ni log Ni minus Gi minus 1 log Gi minus 1 minus 1. Say this is the equation 4. Then we differentiate equation 4 and we use the most probable condition. We look for most probable condition, W becomes equal to W maximum, and if we take its derivative and log, the term becomes delta log W equal to 0. Hence, we differentiate equation 4 and use the most probable condition, delta log W, one side of the equation becomes 0. Therefore, summation bracket term we write here, the derivative of log Ni plus Gi is 1 by Ni plus Gi into delta Ni. Then keep log term constant and differentiate Ni plus Gi. In that, Ni derivative is delta Ni. Hence, log Ni plus Gi delta Ni. Minus, here for Ni log Ni, differentiate log term Ni by Ni delta Ni. Secondly, differentiate Ni term only. Keep log Ni fixed, log Ni delta Ni. And derivative of Gi minus 1 and its log term becomes to be 0. Other side equal to 0 since delta log W is 0. We simplify again here. The first term Ni plus Gi divided by Ni plus Gi delta Ni. It gets cancelled, numerator denominator cancel, we get simply plus delta Ni. And here is minus delta Ni. If we cancel Ni numerator and denominator, delta ni plus minus delta ni cancel, and remaining term is summation log ni plus gi minus log ni. Outside bracket we take delta ni equal to 0. This is the equation number 5. Nextly, we use the conservation of particle and energy. Summation delta ni is 0 since n is constant, and if total energy U is distributed for n number of particles, then summation Ui delta ni becomes equal to 0. Equation 6 and 7 we use here by multiplying minus alpha to summation delta ni and minus beta to summation Ui delta ni, and both the terms we add in equation 5. Equation becomes summation log ni plus gi minus log ni, and these two terms we add here. Therefore, it is becomes equal to minus alpha minus beta ui delta ni equal to 0. Simplify it again. Summation sign cancel on the other side. Therefore, bracketed term becomes only log ni plus gi minus log ni minus alpha minus beta ui bracketed term delta ni equal to 0. In that, whether delta ni equal to 0 or bracketed term equal to 0, but delta ni never 0, hence bracketed term must be equal to 0. Simplify this term. Log ni plus gi minus log ni, that is log a minus b. We write log a by b, that is log ni plus gi by ni minus alpha minus beta ui equal to 0. Separate alpha beta on the other side. Log ni plus gi by ni equal to alpha plus beta ui. And cancel log on this side, one side. Automatically other side becomes exponential. Here ni by ni is 1. Gi by ni is keep as it is, equal to exponential alpha into exponential minus beta ui. Since power addition we take alpha plus beta ui. To take the exponential, we write two separate terms, e raised to alpha, e raised to beta ui. Gi by ni equal to e raised to alpha, e raised to beta ui. This one take on the other side, therefore it is minus 1. We have to simplify ni only. Hence, ni equal to gi divided by this other side gets denominator e raised to alpha e raised to beta ui minus 1, or ni is equal to gi divided by e raised to alpha e raised to ui by kt minus 1, where beta is constant and its value is 1 by kt. Therefore, the equation becomes ni is equal to gi divided by e raised to alpha e raised to ui by kt minus 1. That equation A represents Bose-Einstein distribution law using most probable condition. Thank you.